Welcome, everyone. For those of you that don't know me, I'm Anjali's advisor, Sean Andrews. So I will just quickly introduce Anjali. I don't have an awesome stand-up comedy routine like I did the last time I did this because no one has made fun of you in the literature yet. So Anjali's had a very interesting history, I think. Different than most students, although I found since I came here 10 years ago that the Harvard students tend to have very interesting lives. But so Anjali's been thinking about astronomy more or less for a long time. She worked on the Mars rovers as a high school student. Went to, I won't bring up Jeopardy. She was an undergrad at MIT, and then she went to Cambridge as a Marshall Scholar to get a master's degree with Radial. And then she came here and worked with Ruth Marie Clay on atmospheric escape from nearby or close-in exoplanets, which she gave a TED Talk a few years ago, right? 2 years ago. Which I always find funny because I find these things like almost impossible to watch when they're actually about astronomy. Although in other subjects they're totally fascinating. So that's the point. But I looked this morning and that TED Talk has been viewed more than 1 million times, which is completely mind-blowing to me. I mean, in terms of impact for astronomy, that's a lot. So then after her research exam, she switched to working with me, and the sort of timing of that was basically a change or a pivot in the way that I was thinking about the kind of science that we do on protoplanetary disks. And it was really just, I was sort of a little freaked out by something that I helped create, which was sort of detailed radial transfer modeling of observations, which has sort of run amok. Now people write papers where they have full-page tables of parameters, and the models don't look that great compared to the data. So Anjali's project sort of sprung from the idea that maybe we should take a big step back and try and think about the data more directly, with the goal of being able to sort of do demographic studies in a more empirical grounding. So I think that's worked out really well. I hope she agrees. However, in the middle of doing this, she conveniently decided to take a year leave and go and work for the White House as a White House fellow. And I remember when she was applying to this program, she came and talked to me about it, and Doug as well, I think, right? And we were both very encouraging. And she was like, "Oh, I'm not going to get this," which is sort of like a typical student thing to say. So I'm going to apply for this, but I won't possibly get it. And I was like, "Oh, I don't know." And then I looked at the list of the people who had gotten it before you, and I distinctly remember it in a lapse of being a good advisor, saying to her, "Yeah, you're not going to get it." I sort of regret that, but I think it was like, it wasn't from a mean place. These are incredibly competitive fellowships where you basically become a government employee for a year. And you should go and look online and see the people that she served with and the people that came before her. It's an incredibly impressive list of people. I don't remember anyone famous. Colin Powell.
Doris Kearns Goodwin, Chris Chiba.
Yeah. It's an incredible program. So she went and worked starting in August of 2016. Started working in the Obama administration in the USDA. And then in January of 2017, she shifted to the Office of Science and Technology of the President. And worked there until the following August. So she came back for the fall and finished up her work on protoplanetary disk. Such an easy set of transitions. Anyway, so I'm going to let Anjali talk about her thesis work, and then afterwards we'll take questions. Thank you.
All right, thank you, Sean. Can everyone hear me? Great.
So today I'm excited to be here with all of you, hopefully in my last hours before being a doctor, but we'll see how that goes, to talk about the work I did with Sean on protoplanetary disks and how we can think about the origins of planetary systems with these observations. So today's an origin story. It's not going to be a complete story of the history of planets, but before we talk about the origins of planets, let's talk about one part of that planet, and that's actually me. So I would not be here today if it were not for my wonderful family. So on the left is actually my mother's mother back in China before she went to Taiwan in the 40s. On the right is a picture of the house where my father and uncle, who are both here, grew up in. This is actually my last name right here. This is a sign for his father's law practice. And it's from the most unlikely of circumstances, right? From Taiwan and India that my parents met in California, and I grew up as a valley girl with the most loving family that one could ask for. So I'm very grateful for all of their support and for being here today. So fast forward into the future, and I've had some amazing mentors. And again, this is an origin story. So this is about the forces that shaped me into who I came today. And again, you can apply this in a few minutes to talking about planets and the forces that shape planets into the way they became. So if every planet had folks like this, it would be a great planet. Yes, Doug, that is your picture, so for better or for worse. And so on the left is a middle school science teacher, one of my first science projects. In the middle is Kim Bernard, the scholarships coordinator over at MIT, who encouraged me to apply for this White House Fellows program. Not everyone.
I didn't actively discourage it.
And Doug, who has done all kinds of things like take me up the sides of mountains. And so this has led to some pretty amazing opportunities. Sean already mentioned this. Last year I had the opportunity to serve in both the Obama and Trump administrations with some of the folks who are here with us today, including former fellows and some of our interns who are actually at OSTP. So I'm lucky to have both colleagues from all parts of the spectrum. But of course, all of these forces really led me to challenging situations and opportunities that New England has to offer. And I don't mean climbing mountains, I of course mean the PhD. So it would not be possible to be here and do all of the great work that I have enjoyed watching other people do, and also I've participated in part without all of the amazing faculty, the staff, the administrators, Peg, Rob, and others, and of course the graduate students, who I know there is this trend amongst graduate students during a PhD talk to look for your name. So good luck finding your name. You should probably find it there, because I think it's a whole community effort, and so it wouldn't be fair to just single out a few people, although I have had some pretty extraordinary classmates and office mates. But of course, again, origin stories should ideally end with where we are today, and that is this defense. So I've been advised by Sean Andrews, who has made sure that I've been well informed, not just of literature, but also of popular culture. So this is a scene from 2001, A Space Odyssey, which Sean made sure I watched when he heard I hadn't. So really, this is a very full service degree. And I've had the privilege of being mentored by Doug and having my thesis committee support this work and make sure that it was on progress. So Dimitar, David, and Joan, thank you for coming out from Arizona. This work has enjoyed collaborators who are at the CFA or were at the CFA, and you can see their names listed here. And of course, there are facilities and funders that make these things possible. So that's the origin story of how I got to be here. And when you look at the stars at night, what you're seeing are actually the hosts of many planetary systems. Because planets, it turns out, are common. That one patch on the sky alone shows some of the thousands of planets that have been discovered with the Kepler spacecraft, a lot of that work done by the good folks here. And these planets are actually not just common, which is mind-blowing still to me, but also remarkably diverse. Each of the colors represents a different sized planet. We discover planets of sizes that we don't see within the solar system, and we discover all these other characteristics that are still remarkably different. So the question is, what is the origin story that made all of them with their great people or not on them? So we can take a step back and look at this view of the night sky with Magellan. This is an observatory that many folks here use. And what you can actually see in this picture is what philosophers in the 18th century used to think about planet formation. And that is actually that there are 3 planets shown in this picture: Jupiter, Mars, and Venus. And you note that they're in a line. And people saw that the planets were orbiting around the sun in the same direction. And actually, they're very flat in their orbit, like a pancake. So that's why you see them in a line. So Kant and Laplace and others posited that the planets formed in a disk of material that was rotating, called a protoplanetary disk. We can't see this protoplanetary disk anymore in our solar system. Our planets are fully formed. But we would love to understand planet formation by studying protoplanetary disks that are still in existence around other stars. It turns out that this is something that is very possible to do. So with the benefit of the Hubble Space Telescope, we can look in the Orion constellation at the Orion Nebula. And so all of this gas that you see here in these beautiful colors, this is an image that was taken in visible light, in the optical. And you can start to see that of this gas in the young stars, there are actually these 6 regions that are highlighted in the inset. And each of those is a protoplanetary disk. Dozens of protoplanetary disks have been discovered within the Orion Nebula. And I'll just talk about the one on the top for a moment. Because what you see there is there's this bright background, and the protoplanetary disk is absorbing its light. So it's blocking some of that. So if you want to see what's happening in a protoplanetary disk, visible light isn't going to allow you to see what's happening inside. But again, I want to know its origin story. So what's happening inside? Well, thankfully, artists can help us imagine what that might be like. That's not maybe what you thought we were going for, but we'll get there. So what I'm going to show you is a movie of if we could zoom in to a protoplanetary disk, what does this look like? So you can see a disk of material around a young star. It's rotating. And as we zoom in, you're going to see the constituent components of the protoplanetary disk. So a protoplanetary disk is about 1% solid material and about 99% gas. So that's why you see what looks like wind streaming around. And as you zoom in, you can see that there's solid particles of all kinds of sizes. So there's some big particles, there's some little particles. You'll actually often hear me talk about dust, and I'm just talking about some of the smallest solids within the protoplanetary disk. And these solids are colliding. You can see that sometimes they bounce off of each other, sometimes they stick together. And the sticking together is one of the mechanisms in which these solids can grow larger. But the thing is, growing is hard. It's not guaranteed. So on the right, I'm showing a plot of what the outcomes of 2 particles of different sizes colliding is. What you should take away from it is the colors. It's like a stoplight. Green means grow, red means don't. So this is a legend to help you understand what's on the right. On the left, the legend is in order of increasing collision velocity. So you can see that at low speeds, it's easier to stick together. At higher speeds, it isn't. So the plot on the right shows you the results for what a collision's outcomes could be at one particular location in a protoplanetary disk. At different locations, you'll have different outcomes. But the main point is that it's hard, right? If you, for example, at this location in the disk are greater than about a centimeter, and you have 2 particles that are the same size, there's no way for you to grow larger. But if you had particles of uneven sizes, maybe a little particle and a bigger particle, the little one can actually go at high velocity and stick with some of its material adding to the bigger particle and a little bit of it breaking off. So if you go out today later and take a snowball and throw it at a tree, some of that snow that sticks to the tree is like the process of mass transfer. But again, I just want to emphasize that growing these solids larger is hard. And it gets harder because there's the interaction of the gas and the dust in the protoplanetary disk at play. So on the left is a schematic that I've drawn of what a protoplanetary disk looks like. So you see the star at the center. It's hotter closer to the star and it's cooler further out. And similarly, the densities are higher towards the center and lower further out. So if you imagine a force diagram like you did in high school physics for a particle on the orbit drawn with the white dashed line, a solid particle, the dust will actually feel gravity inwards, and it'll be moved outwards from rotation, and it'll then orbit at Keplerian velocities around, hence the VK. The gas, however, has a more complicated story. And that's because the pressure, because of the temperature and the surface density decreasing with distance from the star, mean that the pressure is actually also going to fall off. And if you look at this equation, you can see it depends on how the pressure changes with radius. So in this picture, you can see that the pressure smoothly decreases with radius. And so dPdr is negative. If dPdr is negative, that means that V gas is less than V Keplerian. And as a result, your gas is moving slower than the dust is moving at. So that means, like, if you stick your hand out of a car window and you feel that headwind, it's the same process for the solids in the protoplanetary disk. They feel a drag force from the gas. And this process causes them to actually drift inward towards the star, called radial drift. So the problem with radial drift for growing particles larger is that it means that you might be drifting fast enough that you drift inwards before you have time to grow larger. And this is a very fundamental timescale problem for the story of planet formation. The size at which, the rate at which a particle moves inwards depends on its size. And so you can see if you're further out, you have really significant velocities inward if you are a millimeter-sized particle, for example. And so this is actually an unsolved problem in planet formation, right? How do you overcome the drift barrier and manage to grow a planet? Because the theory of planet formation is such that you started out with dust that was microscopic sized. So you can think of the dust actually as being like smoke particle sized. It's actually a good visual analogy. Going up to being millimeter sized. So courtesy of the Geology Museum, I actually have some meteorite samples that you're all welcome to come and look at afterwards. You can touch them, it's fine. I checked. And so, for example, I don't know if any of you can see in this, but there's little white flecks. For example, in this meteorite, you can also see round inclusions in this picture of this meteorite that I took earlier. And those are millimeter-sized particles that have been melted and captured in a meteorite and brought here to Earth. So that's actually left over from the solar system's formation. So again, you got from these microscopic particles up to millimeter-sized. And then something happens that things continue to grow to get to the kilometer-sized asteroids and up to the terrestrial planets or the cores of the giant planets that we see today. But there is some ambiguity about that missing step. So as Sean mentioned earlier on, my work is thinking about how can we use observations of protoplanetary disks rather than theory to help us understand this growth process. So I'm going to talk about 3 projects today. The first is about how you leverage observations taken at multiple wavelengths to understand something new about protoplanetary disks. And then I'll focus on leveraging observations of many disks. So we'll focus on a single frequency, but we'll look at a survey of 50 resolved disks. And finally, we'll talk a little bit about how you can do a better job of modeling your observations. So first, the multi-wavelength observations. So the goal of what we're trying to do, and I'll break this down as we go, but is to measure how the spectrum changes radially for the disk around the system called UZ tau east, to get some sense of that growth of solid material. So UZ tau east is a binary system, shown in the middle here in this optical image from the Sloan Digital Sky Survey. And what's remarkable about it is it has this very extended, bright protoplanetary disk around both of the stars. It's fairly low mass for the combined mass of the system, 1.3 solar masses. And it's in Taurus, so it's reasonably far away, but it's still accessible. So it's 140 parsecs, and it's maybe 2 or 3 million years old. So what you can see, if you look at the spectrum, so this is a plot. You'll see a lot of plots where I talk about a spectrum. That just means it's a function of wavelength or frequency on the bottom, is how the light is distributed on different scales. So you can see that in the visible, the spectrum matches what you would expect for emission from a star. But as you go out to longer wavelengths, so in the infrared, the red shows you Spitzer Space Telescope observations in the infrared, and out to longer wavelengths in the microwave, you can see that there's more light from UZ tau east than you would expect just from stars. And this is actually emission from the disk, because all of these little solid particles and bigger are actually heated by the star, and they re-radiate light. It's the thermal emission that we are seeing in the spectrum. And we can think about how the shape of that spectrum changes as a function of the different kinds of particles that are emitting. So the equation that shows you a little bit about the spectrum is that in the limit of optically thin emission, so we can see into the disk how much material there is, it's the product of the Planck function, the dust opacity per unit mass, and the surface density. So you note the two functions on the left, the Planck function and the opacity, are both functions of wavelength, right? The surface density doesn't care what frequency or wavelength you're at. The Planck function has some well-known shape. It's similar to that blue shape that you see there. But the opacity actually will vary with particle size. So on the right, I'm showing you a plot of the opacity per unit mass on a log-log scale as a function of wavelength. And as the particle size increases, decreases, you can see that the opacity spectrum gets steeper. So if that's getting steeper, and the plot on the left is supposed to be the product of different things, you can see that this slope in the millimeter, or in the microwave, is controlled by the slope of the opacity. So larger particles will have flatter slopes, and so lower values of alpha, and smaller particle size distributions will have steeper values of alpha because it's a steeper slope. So we can actually look at what the alpha value is in a myriad of nearby protoplanetary disks. So if you measure the alpha values for all of them, so there's alpha shown on the y-axis, on the x-axis I'm showing you the flux density of each of these sources. So each of those points is a particular disk. And the main point I want to get across is you can see that most of their values are lower than the alpha value for the ISM. So that is to say that particles within a protoplanetary disk have somehow grown larger than what you would find in the space between stars. So this point about disk solids being larger than the ISM is a good starting point for our story of planets being formed from solids that are growing. But what can we see within the disk as a function of distance? So on the left, I'm showing you the surface density as a function of radius. And it turns out that those processes of radial drift inwards and grain growth both predict that you should find larger particles closer toward the star. So that's why you see the centimeter particles at small radii and micron-sized particles further out. If you have these size sorting happening like this, then that means that you should also expect to see that the shape of the spectrum will change with radius in the disk. So closer in, you'll have big particles and a lower alpha value, and further out, you'll find a larger alpha value with the smaller particles. And so we expect to be able to look for, in our observations, alpha increasing with radius. So a word about our observations. So I've mentioned that we're looking in the microwave or the radio spectrum. These disks are on order 100 AU across, and they're 140 parsecs away. So this means that a disk should really be observed with a telescope that's a few hundred meters or even kilometer sized in order to observe what we're looking for. Building a kilometer-sized telescope is challenging, to say the least. And so we can leverage interferometry, which is adding telescopes at different distances together to combine to simulate one large telescope. So this is a picture of the Very Large Array in New Mexico. So if you've seen Contact, that's what this is. And you can see that they're quite far apart. So the VLA is actually one of 3 facilities that I use. You remember I acknowledged them at the beginning. So the VLA allows us to have our very longest wavelength or shortest frequency data. So we get out to 5 centimeters. We also use data from the KARMA facility, which gets us around 1 millimeter or 100 or 200 gigahertz. And out in the top of the plot, you see the sub-millimeter array, which gets us 0.88. It's less than 1 millimeter of observations. And again, I remind you that we use all of these observatories so that we can measure how the spectrum changes to understand particle growth. So here is a view of the images that you get with these telescopes. So in order of increasing frequency, so all of these are views of UZ tau east for 3 arc seconds on each side. The size of your beam, so basically your resolution is shown in the lower left of each panel. A scale bar is shown on the very left plot. And of course, because Jim is here, we have to show the visibilities. So what you're seeing in that second row is actually the same information as on the top, but this is actually what the telescope measures. So the data are the black points. They've been binned. And we fit a model to the visibilities. So before I show you the model, I just want you to note the visibilities are the Fourier transform of what's on the sky. So something narrow, like I've shown you in the bottom left corner, something narrow on the sky is a broad visibility. So over here, you can see that the visibilities have a narrower feature than out at low frequency. And that means that on the sky, that's actually smaller, and this is bigger. And you can look at the images in the top row, and that agrees. So, and again, the reason it agrees is it's the same thing. So we fit a model to the visibilities that assumes you have a flat disk that's azimuthally symmetric, so it's the same as you go around, and it just varies with radius. So we want to measure what is the brightness as a function of radius. And so all of those blue lines are based on the models that I'm showing in the bottom row. So there you see the logarithm of the surface brightness as a function of radius on a log-log plot. And you can see that the intensity increases with frequency, and you can see how that varies. So we wanted to use the surface brightness as a function of radius to be able to compare the spectrum at different radii. So if we stack all of them together, what you see on the left is just all of those combined. And on the right is we're measuring alpha, right? Since alpha is a slope, you can get there by just taking the ratio of the surface brightness on the log scale, the ratio. And so if you take the ratio of the light blue line and the red, 225 gigahertz and 30 gigahertz, you get the plot on the right. You could get a similar plot for any other choice of values, of frequencies, or you could fit a power law to all 5 of them. We chose those 2 because those have the same resolution. So on the right, though, you can see that alpha increases with radius. And as you recall, this is what we expected to find, because if you had bigger particles closer in, you should see a flatter slope, and that spectral index value should be lower because your slope is fine. So Sean mentioned in his introduction that there's been a lot of focus on, or I think you said it ran amok, with radiative transfer calculations. So measurements of the spectral index have been made for a handful of disks, fewer than 10, including this one. And all of the other studies, apart from this one, use physical models. So they model what the opacity is, they model what your grain size distribution is, and what the temperature. So they've imparted what the physics are and compared what you get out. But you notice I didn't have any physical modeling to get us here. So if our physical models were, say, wrong, it doesn't actually change what we get here. But that also means that you don't really even need to look at the spectral variations in alpha, because you could just look at the surface brightness profiles, and again, for you, Jim, the visibilities. Because remember, I showed you that these are narrower, which means they are actually larger on the sky, and those are smaller. So we can think about this by using another metric, the cumulative flux. So what I'm going to show you on the right panel is if we integrated the amount of light under the curve on the left as a fraction of the total flux, where is the emission concentrated? So here we go. So if we sum up the flux, it starts at 0 and it goes out to 1. And you can see it's got this sigmoid shape. So this means that we can pick some particular value of the cumulative flux. Say we want 68% of the total flux. And we can find the radius that corresponds to that location. So that means within row F, I have 68% of the total flux of the disk. So this is just a way of quantifying the size of the disk. And if we look at this, for all of the surface brightness profiles that I showed you at the 5 frequencies, you can start to already see that they're separated out spatially, right? The lower frequencies are on the left, the higher frequencies are on the right. So if you calculate those effective radii and plot that as a function of frequency, again on a log-log plot, you can see that they increase with frequency. And this is just another way of thinking about the particle size segregation, because if you had your bigger particles closer into the star, you should actually see the location where they are as being smaller than the location of the larger particles. So this is to say that this project on using observations at multiple wavelengths gives us ways to think about particle size segregation and measuring the spectral variations radially, but We can also just encapsulate that in a nice, easy to understand size-frequency relation. So that's something new to think about. So we'll come back to that more later, but I now want to focus on leveraging a different technique. So instead of leveraging multiple frequencies, we're going to leverage multiple disks to do a demographic study. And the key to this one is using that same size metric that I just showed you and applying it to a suite of 50 disks. So this all uses the submillimeter array. So this is an observation, a set of observations done at 340 gigahertz. One of the great difficulties for my non-astronomer friends who are here of being an astronomer is sometimes you have to go to Hawaii to use telescopes. So I'm very grateful that I'm at an institution that has given me that opportunity. And so the 50 disks that we observe for this survey, 10 of them are new to this work, and others are from the archives or past work. So the ones that are new are shown in orange. And we'll come back more to this in a minute, but you can see that there's a bunch of different shapes. For example, you can see holes in your disks. You can see that there are brighter disks and smaller disks. And there's a lot of information encapsulated here. And the question is, when you make observations of many protoplanetary disks, what can you do with that? So historically, what's been done is to look at the total luminosity of the disk. Because if the emission is optically thin, then the surface brightness goes as the surface density, and the luminosity will then scale as the mass. And you might wonder, why do you care about the total mass of the disk? Well, if you want to form planets, you want to know how much material there is available for planet formation. So on the left is one of the earliest studies of millimeter emission from a survey of disks done by Beckwith et al. So both on the left and right plots, you see the disk mass as a function of the 1.3 millimeter flux density. So on the left, that was earlier, and on the right, it's from 2013, but it's still, most of those disks are unresolved. And you can see that as you vary the spectral type, you can start to see trends. So with a survey, you're hoping to understand something about the demographics that went into it. And a lot of them have focused on this indicator, which is the luminosity or the disk mass. When there were resolved observations, there was a hint from both Sean's 2010 study and another group's 2014 study that showed if you measure the size of the disk, that actually tends to increase with luminosity, or the 1.3 millimeter flux, as you've seen here. So what I was doing with this work is applying that same size metric I used earlier, but to extend this relationship out further with our survey of disks. So that size metric that I showed you earlier, as a reminder, is just measuring the radius that encircles a fixed fraction of the total flux, and it has a couple advantages. So the first is that we can use it to compare different studies, because Sean's previous work encapsulated size as a model parameter, the characteristic radius, so it depended on that particular choice of surface density profile. If we did that for the profiles that I'm showing on the left, those actually both have that same model parameter value, rho t. So we've chosen different models, that's why that one's rho t and this is RC. And it's hard to compare different studies if you're using different model parameters. So one benefit of ours is you could apply that to any model you wanted and make some comparisons. But the other thing is that it better encapsulates what you think of as a size. Because you notice on the top that the emission from the green disk is actually out to longer scales than from the blue. Right? You see more light further out. So you might say that the green disk is bigger. If you measure the effective size for both of these disks, you find that the green disk does have a larger effective size. So this metric more intuitively captures what a size means. But the other thing is, it really doesn't matter what model you've chosen. So it isn't just that you have a metric that can be applied to any data set. As long as you pick a model that reproduces your data well, you can measure an effective size, and that's great for these demographic studies. So again, we're going to use that size metric to measure the sizes of all of these disks. And I'm giving you one more view of them. We're going to say goodbye to these two momentarily because they will not fit on my future slides. So just as a note, in case you're wondering where they go. And I've highlighted on this slide with the blue stars the disks that were used in Sean's earlier survey, where you saw that hint of the size-luminosity relation. So we can use our surface brightness model to make 1D models of the brightness for all of these. And again, those two are gone. So here's 48. surface brightness models, you can see, just as you saw here, that there are all kinds of shapes. Sometimes it's darker in the middle and brighter further out. Sometimes it's monotonically decreasing. So we have a way to model all of these, but what we're really interested in is the cumulative flux and the effective size. So we can measure that for all of these disks, where I've drawn a dashed line to show where 68% of the flux is enclosed within that radius. And you can see the spread on these. It does a good job of encapsulating the uncertainty you actually saw in this earlier image, because of course some disks are more resolved than others, and those uncertainties are well captured by the uncertainties in the cumulative flux. So if we measure the effective size for all of these disks and compare that to luminosity, we do in fact see that there is this trend. It turns out that if you look on this log-log plot of effective size as a function of luminosity, that the luminosity actually goes as the effective size squared, or as the area. So that means that you have this constant surface brightness within your effective radius, which is very interesting and intriguing. So we'll talk more about what that could mean in a second, but I just wanted to point out that since this paper was published last year, there have been further studies from other groups that have added to it. So Scott Barenfeld out at Caltech actually measured the sizes and luminosities of a group of disks in the Upper Scorpius OB association, and those are the points shown in blue. And you can see that they actually lie along the same scaling that we found. And moreover, some work with the lupus survey that you've been hearing a lot about lately, that Sean is working on, tentatively, that also agrees with the scaling that you see here. So it's amazing how we're already starting to see with the survey of resolved disks some trends that we can now get to work theorizing about. So Avi, you have some work to do. So these are showing how observations at multiple frequencies give us a size-frequency relation. Observations of many disks with resolution gives us a size-luminosity relation. So the question is, what does theory, before Avi gets into this, tell us? And the answer is we can use models from Sean's former postdoc, Till Bernstein, that take into account a gas disk that's viscously evolving with dust embedded in it, and see how that evolves over time. And does the model compare to our observations favorably? So here's just the disk from our sample with the scaling, and you can see Till's models in those blue, red, and green lines. Don't worry, they'll get brighter. So what you're going to see are, I've just modeled, I've chosen 3 models with different parameters, so you can change the size of the gas disk, the mass, and other properties. And over time, we can look at the output for the size-luminosity relation from his models. And what we find is that at early times, it actually does a reasonably good job of reproducing what we find. However, at later times, it starts to go off in a different direction from what we expect to see, or what we see. And it's interesting because all of the disks in our sample are a few million years old, so it's more like the brightest colors, 2 or 3 million years old. But the models fit better actually at earlier times. And so that suggests that there's something that's not quite right here, right? We need the models to actually slow down a little bit so we can be matching at a slower age, a younger age, or a different slope. So before we interpret this, we should also just compare to our size-frequency relation, because you remember the size-frequency relation agreed with what we expected for particle size distributions. And the same physics of grain growth and radial drift are encapsulated in these models. So you can see if I run a grid of models with different parameters, I can pick out a handful that happen to match the size-frequency relation. I've highlighted the ages of the snapshots that I've pulled out, and you can see that at a range of ages, you can reproduce the size-frequency relation. So that's good. But what's interesting is if you look at the spectrum for those same models, you can see that our data points are actually best matched by a normalization of 1 megayear or less. But UZ tau east is 2 or 3 million years old. So why don't those blue points match? More to the point, you can see that the slope is different. It's shallower, which you remember is an indication of larger particle sizes. So there's something going on here, both in this and in the size-luminosity relation, where the models are too fast. You need some way of slowing them down. So all of these models have assumed that you have a smooth disk of gas. where the pressure monotonically decreases with radius. So you remember that when dPdr is negative, the gas moves slower than the dust, and as a result, it acts like that headwind on the dust, so it gets dragged inwards. So that's what's causing that rapid radial drift. But this is a really cool plot from Fred Whipple, who used to be here in 1972, where he said, well, what if instead of just having a smoothly varying pressure profile, there was actually a pressure bump? So if you have a pressure bump, then that means that dPdr is 0 at its peak, and dPdr is positive on the interior of that pressure bump. So that means in this equation that the gas will be orbiting at the same speed as Keplerian at the peak, and actually faster interior to that. So that means that the dust particles are actually going to be concentrated inwards towards this pressure bump, right? So whereas outwards they're moving in, here they're stopped, and here moving in. So this gives you some method of slowing down radial drift and migration. And again, I think it's really cool that this is from 1972 here. So what happens if we model a disk with these substructures of pressure bumps? So we can arbitrarily find a model that will, in fact, get you the right relation for the size-luminosity relation. And that's just showing that it is a possibility. I'm not saying that's what it has to be, but it's possible. The other thing you recall is that the luminosity goes as the area. And that's actually, if you think about what happens in optically thin versus optically thick cases, this can be indicative of optically thick emission because there's no radial dependence when it's optically thick. And so that's why we actually plot what you would expect for optically thick emission. And you can see everything is to the left of it. And that's good because if it's to the right, you can't get more emission than when it's optically thick. And just as an upper bound, if you had a 10% filling factor, you can see where that lies. So I want to emphasize that this is actually really intriguing because previously, if you're familiar with the example from The Little Prince, where, if I show you this picture, someone might say it's a hat, and someone else will say, no, it's a snake that's well fed. It had a healthy pachyderm diet. That previously we were saying we were looking at the total disk mass from the luminosity because it was optically thin emission. So basically how bright something was gave you an indication of what was in it. But if it's optically thick, how bright it is has no bearing on what's inside. So maybe we're looking at more of a hat than an elephant. And if this is the case, this actually changes our interpretation of other observables. So on the left is that same plot of the spectral index as a function of radius for UZ tau east. It's now on a linear scale. And on the right is one of the results from Jane's recent paper from some high-resolution observations from ALMA for the disk around TW Hydra. So what's shown here on the far right is actually a map of that spectral index, if you could see it in 2D, not just in 1D. So you can see that Jane actually has much better resolution than we do, right? That's much smaller than this. So you can imagine if you went with that beam size and smeared over this, you might get what you see on the left. So maybe what we're seeing is actually just unresolved substructure, because you can see all of those features in Jane's spectral index plot. But the other thing to note is that you can see that alpha is roughly 2 at small radii. Alpha of 2 is an intriguing number because, of course, I see Avi nodding, so that's good. In the Rayleigh-Jeans limit, you expect the spectrum to be alpha of 2 for blackbody emission. So it's possible that everything that I told you at the beginning could just be the hint of something more, right? Maybe it isn't just a sign of particle growth with radius, but something that we're not seeing at low resolution. So it turns out that if you have high resolution observations with ALMA, you do actually see that there's an abundance of substructure. And in fact, it might be universal. So you can see the observations, for example, on the top right from Sean's result for TW Hydra, where because TW Hydra is so close by, we can actually see down to 1 AU scales of substructure, which is really remarkable. I remind you that our distance from the sun is 1 AU, so think about that. And you can see that there are bright rings and dark gaps and even spiral arms. And I remind you that in our survey at lower resolution, this is what we saw for such disks. You can see that we aren't able to capture that substructure, but at high resolution, it's actually there. So the fact that in the size-luminosity relation we've said, well, maybe you could explain that with substructure, and similarly for your alpha variations, agrees with what you expect at higher resolution. So in these two observational projects, I've described how by using this empirical size metric, we can encapsulate some properties of the disk in a size-frequency relation if you have observations at multiple wavelengths, and if you have many disks but only one frequency, the size-luminosity relation. And all of this, though, has been using the assumption of models of a smooth disk, right? But what happens if we wanted to do better? We want to move beyond this smoothly varying profile for a protoplanetary disk and have some way of modeling something that has dark gaps or other features. So ideally, you would say, I know there's a dark gap right here. It has this width and this depth. And then you can, again, Avi, go to town having theories to explain what might cause them. So our method is going to show you, I'm just going to show you what the key to this method is. So on the left is a surface brightness profile. On the right, the visibilities. Again, it's just a simple Fourier transform between the two. And this is a Gaussian profile, which is very nice to Fourier transform. It turns out that if you take that surface brightness profile and discretize it into having constant brightness in a bunch of annuli, that's something that we can easily Fourier transform as well. In the limit of infinitesimal annuli, infinitesimal rings, it would be an exact reproduction. But you can see that even with some discretization, you can recover the visibilities. So this means that instead of using a parametric model that has maybe some power law index and some characteristic radius, now you're just going to figure out how bright is the surface brightness in each of these annuli. Those are going to be your model parameters. So the number of model parameters you have is decided by how many annuli you choose to use. So one example of this is if we simulate some ALMA observations that I showed you earlier on the right with the gap. I know what I put into that, and so the truth is actually this black line. And what you can see from our model is shown in blue. So the horizontal error bars are where the annuli are placed. That's not an uncertainty. That's just a demonstration of the radial extent. Whereas on the y errors, those are actually the uncertainties. And you can see from this plot that actually we're able to recover that gap that I've injected perfectly, which is kind of remarkable. And it's more remarkable when you consider that the image that you see here is shown in yellow. So if I just drew a line on the deprojected image and calculated what is the average surface brightness at each radius, you get the yellow. And this is remarkable because you see that that depth of that gap is narrower, is shallower, and it's broader. And that's because the image is like convolved with a PSF, right? So you're smearing out what's truly there. So if you just wanted to create a model using your image, you wouldn't reproduce what's truly there in those gap depths. And I say this because if you look at, for example, HL tau observed with ALMA as part of the science verification data, the image is shown in yellow, and some preliminary results from using this model are shown in blue. And you can see that at all of the locations that the discovery paper finds these dark gaps, so those are shown with the dashed vertical lines, you can see that we actually start to find deeper gap depths. So more work is needed here, but it's fun to think about how with this model, where we haven't assumed anything about the disk a priori, we're actually able to uncover some of this substructure and quantify it. And the goal here is to be able to appropriately model our observations so that theory and observations can be brought in line with one another. So I mentioned earlier that we have these two hints of substructure from the size-frequency relation and the size-luminosity relation, which we were modeling with smooth structure. But with this method, it actually gives us a way that with more work, you can actually start to add those back into your theoretical models and bring them back into alignment. With that, I'll stop for questions. And I remind you, you can look at meteorites afterwards up close. Thank you. I took out a bunch of stuff last night.
Okay, question.
Alyssa.
Do you want to manage your own question?
Sure.
Anyway, that was just an astonishingly beautiful talk. and also then I have a question, which is you showed very nicely the correlations of the dust opacity and the radius. And then you showed that there are these gaps and that you can model them, but what if, or maybe it's already in the model, but if there's a correlation of the opacity with the local environment, whether you're in a gap or not, is that taken into account in the model, or is the model kind of agnostic to that? In other words, you have surface brightness and opacity, and they multiply together and get you
Right.
So you have a radial dependence of the opacity, right?
Mhm.
But if the opacity also varies with some local, what would that do?
Well, so for what I did here, though, since I was modeling the surface brightness rather than the surface density, it doesn't matter what your surface density and your opacity individually are doing, because those are both convolved together to give you the surface brightness. Right, exactly. Avi, you had a question?
Yeah, so the simplest model that one can think of, and I want you to tell me that it's ruled out, because it sounds very simple and it's not, you don't have to worry about the details, would be that there is some energy impinging on the disk from the star, okay? And the disk is optically thick, and this energy is re-radiated, okay? So we know how much energy is impinging on the disk from the star and then re-radiated, so we can figure out the temperature as a function of radius, and that will give you a luminosity radius relation of the type that you mentioned. So is this simple model ruled out? An optically thick disk which is illuminated from above, and therefore its temperature structure is dictated by that.
So I think that that's actually similar to what I showed
Oh, it's
here.
similar.
So I don't think it's ruled out necessarily, but I'm not sure.
So in that case, you would not be sensitive to the size distribution of the
Correct.
particles.
Yeah.
And it's not ruled out.
Well, I guess you showed that
It's-
all those, showed the optical.
Right,
optically thick. Sort of depends on what you mean by ruled out.
Yeah.
Observers are more forgiving. The red curve is what you're talking about.
Right.
Right, that's what happens if you're optical. Yes.
And the red curve is calibrated based on the luminosity of the star?
Right. Yeah.
Okay, so for stars, so you can also check stars of different luminosities and see
Right.
whether it agrees. So,
But isn't it
Exactly
also
right.
probably likely that there's a variation in the
Correct. Right. It's not 100% optically
Right.
thick.
thank you.
Other questions? Yeah.
So there's a pretty big dispersion with this luminosity to radius. Is that what? Why is that? Is that saying something about how many gaps there are, or volume of the gaps, or is it something about temperature of the star?
So you're asking about the dispersion, vertical
Yes.
or perpendicular to this line. So you might think that there's some relation maybe to stellar heating, right, in the environment. And it turns out that actually if you account for the temperature of the dust, so the luminosity of each of the stars, and then take some relation for how the luminosity relates back to the mass, just again as a way of encapsulating the temperature, you actually find a nice size-mass relation that has less scatter perpendicular to this. So again, taking into account the stellar activity does help. Other questions? Yes, Elizabeth.
In your model, do you fix the locations of the bins that you're using, or do those vary?
So right now you choose where you want to put your annuli beforehand. If one of you is enthusiastic and wants to find the version of arbitrarily adjusting it, that would be ideal, because where you choose to put the annuli will change your results. James.
I'm curious how the average density of these protoplanetary systems compares to the density of material which is distributed throughout our solar system. So what fraction of material has been incorporated into planets in our own solar system? Yeah. Apologies, a naive question from a non-astronomer.
So the hallmark of a protoplanetary disk is that there's a lot of gas, right? So within our own solar system, we don't have that volume of gas that's left. And then the distribution of solids and the densities, of course, there's it's different is the short answer. Because in the solar system, right, you can think about the asteroid belt or something like that, which is actually left over from collisions of the solid particles. So that's different physics from the regime that I'm in, where you have gas and the particles sort of at an earlier stage. So we can think about what's in the solar system as being what's known as a debris disk, because it's after the fact. Were there any other questions? Raven.
Thank you for the origin story, and I love history, so this is wonderful. Given the trends that you've identified, we can understand that this process is still going on and will continue to happen, right, in the universe. So you've also been able to predict the future, and I think that's wonderful. Are there any particular implications for us here on Earth? Maybe not in our lifetimes, but what does your work tell us about, our lives and what we might expect for generations on this planet?
So I will say, in terms of the value in studying planet formation, so there are people like Dave who do all of the exciting work discovering new worlds and what they're like and, what the atmospheres might be like. And you might think, well, planet formation is a little dull. But it turns out that what you're going to be able to observe...
So just to be absolutely clear, I think this is really...
I didn't say you had said that. Just like Sean is always very encouraging. But it's one of these things where... tough crowd. Where what we can actually observe is actually maybe just a fraction of what's out there. And so with planet formation and evolution studies, we might be able to predict the full, I don't want to say suite, but all of the different kinds of planets that are out there. So with some of this work, you can foretell what you can't even see in the future. And I think with that, I think we'll stop there. But I'm happy to take more questions and come look at the meteorites. Thank you all for coming.